Yeah.
I'll do it. I'll do it. Wait, do you have that other box we just did? The other brown one? Because we should do,
It's probably a crowd.
Yeah, that's a good idea.
No, no, what's another?
It's a good thing, you know, I need that guy.
No, that was my main concern.
One, yeah, I had two, and one of them dropped out, and the other one.
Well, I checked with, that's the most important thing, because if I give an egg, I have to just.
Of course.
So if I give an egg to somebody who's not around, then I have to. Okay.
She's on her way.
She's done. She doesn't care. I'm doing intro. I can do the pros cons. Hey, it would be weird to stop. You want to do 2 slides or 5? Okay. Yeah, you can go to studying stuff.
Yeah, that's a huge. Yeah, like, I mean, just so like. Wow. I mean, you have a lot of, like, I don't know. You're educated. Why what?
Especially for you. Already after.
You're not. I go back.
Oh, it's like this is the. No, it's not.
It's like this, like.
It's also not.
This cute, like little.
I don't think it's looking back.
Who is you have?
They finished their job.
Yeah, I'm still looking.
What? Do what? Oh, yeah, no, you don't question it. I think it's because your mirror live. Mirror suite is now on. Yes, this should be what your computer. You have to set it up and not rotate it.
It's fine. You guys want.
You did it separate.
What is it?
Yeah. Yeah. Okay, that's not good. Check the slide. And I had to. Keep it vertical, and then when we show it, this was,
They're balls.
Like, oh, take a picture.
With the leg thing? The whole. What?
so you're probably going to want a mic.
I just got that.
Go better than.
But I learned from that.
It's better that you not sound like you're shouting and more. I always sound like I'm shouting.
I can project my. You actually speak quite quietly. Yeah, you talk loud. I know.
Alrighty then, can everyone sit down so we can get started? Yeah, but all right, so we are, hope everyone had a good lunch, first of all. We are the Portable Life Support System. I'm Ben Kaiser.
I'm Rishika. I'm a graduate student in bioengineering.
Oh, I'm a graduate student in mechanical engineering.
Kayvon, I'm a freshman in mechanical engineering student.
Hello, my name is Juan. I'm a master's student in mechanical engineering.
Sunny, I'm a mechanical engineering student.
And I'm Natalie, and I'm also a mechanical engineering undergrad student.
I'm Franny, and I'm a freshman mechanical engineering student.
So just to kick things off, I'm going to go over the requirements. So a PLIS needs to provide adequate pressure for the entire body, provide breathable O2, provide, in our case, compressed carbon dioxide for the suit pressurization, because as we mentioned in the helmet section and I believe in the torso section, that our system is going to be two separate pressurized regions, one pressurized using the Martian atmosphere, while the helmet is pressurized using oxygen. So we also need to control temperature and humidity, provide food and water, collection of urine and feces, trace contaminant management, and supply power. One thing I left off this list that in the past would have been left on is communication. So our intention is that with the modern communication technology that we have today, and given that we won't be communicating directly with Houston, we'll just be communicating with each other, since it doesn't make sense for a suit to be able to communicate with someone who would take 15 minutes to communicate with anyway, just to send one message and receive reply. So essentially, we'll just need to be linked up to each other. And from our basic research, it seemed like it would make more sense to just integrate a very small amount of communication requirements we would need to meet into the helmet. So we passed on that job to the helmet team, which they mentioned a little bit. Moving on, I just want to acknowledge the industry partners who were involved this semester in helping us out. Grant Anderson, who came and presented at the class, and also stayed in communication with us via email. Nikolai Musif, he's the lead design engineer at Final Frontier Design. He's Skyped with us a couple of times. Raul Blanco, he's the branch chief of spacesuit and crew survival at NASA over at Johnson Space Center. He has emailed and spoke to us on the phone, so he's been really helpful, as well as Tim Lavery, the director of the World Explorers Bureau, who helped us a little bit with our dense monolithic membrane work. So first I want to talk about one thing that Dr. K mentioned during his introduction, which was the rover PLIS. We knew right off the bat that we did not want to do a rover PLIS. By which I just mean the astronaut has no PLIS. I'm going to be saying PLIS a lot. PLIS, by which I mean Portable Life Support System. The astronaut would have no PLIS of their own. They would simply be hooked up to the one built into the rover. And that might seem appealing because it takes a lot of the weight off the astronaut's suit, which allows them to move around more freely. But ultimately, it really restricts their movement. There are a lot of situations from the pictures you saw in Dr. K's presentation where an astronaut might want to go that a rover couldn't necessarily go. We also don't want to have to worry about several, 100 feet of tether hooked up to the astronaut. However, there are advantages of the rover Bliss that we didn't want to discount immediately. For one thing, when an astronaut, a Bliss can weigh upwards of 100 plus pounds. And if you were doing work all day, an 8-hour EVA, you don't want to have 100 pounds on your back the entire time. And so that was one advantage of the rover Bliss that we really liked, and we thought, well, how can we keep that while not binding ourselves to, a 50-foot radius around the Bliss? So the examples are all around us on Earth. When students go to class, they don't wear their backpacks all class. When a construction worker is on the job, he doesn't keep all of his tools on him at all time. It doesn't make sense really that a worker should have to have everything they need at any time on them at all times. So we figured build the Bliss like a backpack. Make it something that you can take on, take off, and put on repeatedly throughout the day as you need it. This would involve a small tether to connect the astronaut to the Bliss, but it would only need to be 5 to 10 feet because you're always going to have it next to you when it's off of you. Say you're doing work on the ground, you just put it next to you, you do your work, you put it back on, you go to the next site. It also offers the chance, we have not done extensive research into this, and it would require us to collaborate with the other teams, but it offers the chance that the suit can be donned and doffed by one person. Right now, that's not the case. It's a two-person job, and if it could become a one-person job, that would expedite the process of preparing for an EVA. Another option that we left, that the removable Bliss leaves, is to use the rover Bliss on special occasions. Say all you're going to be doing is driving. You wouldn't necessarily need to bring along the removable Bliss because you already have your suit designed to work with a tether, and you could just tether to your Bliss. So our design is going to be focusing on the open loop system, by which we mean the suit would pump in compressed CO2 at a regular rate to keep the suit pressurized while also venting out excess humidity and forcing contaminants that get picked up through the filters. As you can see here, is just the basic flow chart of how it would work. We'll need to pressurize to 4 to 5 psi of CO2 from what I believe is 0.09 psi, which is the pressure on Martian surface. So in a moment, I'm going to pass it on to Jan, who's going to talk about how we would attain that kind of pressure. But first, I'm just going to talk about the advantages and disadvantages of the open loop system. So for one thing, this is a Martian spacesuit. This is not an International Space Station spacesuit. This is not an Apollo spacesuit. We are on a planet. It doesn't make sense for us to not use the environment around us, which is a resource that has never been available to us in space before. So we have an unlimited resource, effectively unlimited resource of CO2 that we could just pump in and pressurize as we see fit. It eliminates the need to store waste, water, for example, sweat. You can actually sweat quite a lot throughout an 8-hour EVA, and to have to carry that around with you is just unnecessary. It eliminates the challenge of leak prevention because we'll be building the suit to leak at a certain rate, so there's no need to worry about it. It's lighter than the traditional Bliss because you don't need to carry around your carbon dioxide tank, or you don't need to carry around whatever it is you're going to use to keep the suit pressurized. And it provides additional thermal and humidity regulation because you have airflow in the suit. Some disadvantages. It does offer a higher energy requirement because you need to be running the compressor. It's complex, and it's never been done before. And we had yet to design a compressor that exactly suits our needs. So if we had a closed loop, obviously the advantage and disadvantage is pretty much reverse. It's less energy requirement, and it's more traditional in that there's been already extensive research done on how to pressurize a closed spacesuit. That's how every spacesuit has been so far. But you have to prevent against leaks. Even the best spacesuit leaks at a very small rate. You need a waste tank, and it's heavier because you'll be carrying around your waste and the carbon dioxide that you use to pressurize. So now I'm going to pass the mic, although he already passed it, on to Juan, who's going to talk about pressurizing the suit, specifically the compressor.
So the open loop idea sounded very appealing to us. It sounded very promising, but we weren't sure if it was actually feasible. And that was one of the main goals that we set for this semester as the listing, was figure out if this is something that can actually be done. And a good place to start was trying to find a compressor that could actually pressurize the Martian atmosphere at 0.09 psi all the way to 5 psi's. And so that's about a ratio of 50. So that's a significant amount of energy. And we were skeptical at first that this was possible. So we started by doing a lot of research on compressors, found that there's many different kinds. They fall under two categories. These ones called positive displacement compressors, which is essentially entrap a gas or a fluid in a contained chamber, and then you reduce the volume of that chamber to physically compress it. But then a more interesting option to us is these dynamic displacement compressors, which work by adding velocity to the fluid to build up energy, and then slowing it down through a diffuser to convert that energy into pressure. And these are much more promising to us because they're, first of all, they're a lot smaller and lightweight, and they also achieve a lot higher compression ratios, more in the range of what we needed. And more specifically, within these dynamic displacement compressors, we're looking to centrifugal compressors, similar to the ones on the Carter's turbochargers. And we tried to find something commercially available, and unfortunately, everything was just a bit too big. Most of these are used in big industrial applications for very high pressures. As close as we could find was a car's turbocharger, but that was still a bit too big and heavy. So what we decided to look into is, okay, would it be possible to design something smaller, customized to our specific needs? And we found a study led by the University of Stuttgart claiming that the recent development of some magnets allows for the design of ultra-high-speed miniature centrifugal compressors, really with an impeller size of about 30 millimeters. The impeller being the rotor that actually spins the fluids that you can see on that picture in the middle. Just for reference, a turbocharger is about 50 millimeters, so 30 millimeters is about almost half the cruise in size. And so that sounds very promising, and we believe that some good next steps for next semester is looking more into the design. There's a lot of challenges that are brought by scaling everything down, especially in terms of aerodynamics, but there are a lot of studies that can help us design something, and we're confident that with more research and more work, we could actually design something that would work for the KC. So then the next question is, okay, so if we have this small compressor that's powerful enough, where do we place it? An option is to place it in the Bliss backpack, which would be convenient because it would be well contained, so it wouldn't be exposed to the Martian atmosphere. However, because you would be flowing gases through it, you would expose the rest of the place to that outside environment. So the alternative is to place it on the belt, somewhere around the waist, and that would isolate it from the rest of the place, and also just lower the overall center of gravity for the astronaut.
Okay, by far the heaviest part of the Apollo portable life support system was the oxygen storage, which included a primary oxygen tank and an OPS system, which was the oxygen pressure system, which was the equivalent of the secondary system. And this whole system in total was about 35 pounds. So given that our goal this semester was to find the heaviest part of the portable life support system and do our best to basically drop the weight without necessarily compromising the functionality, safety, and in this case, the amount of oxygen being stored, we came up with a couple of methods of trying to decrease the weight. One of the methods that we came up with was a swappable canister system, in which case the astronaut would have to switch out the canisters after a certain period of time or after a certain level of oxygen was left in the tank. This would either be 8 one-hour tanks, 4 two-hour tanks, or 2 4-hour tanks. However, couple of issues came up with them right off the bat. What if the astronaut can't do it properly? They're left without oxygen. Or what do you do with all those tanks? You have to carry it yourself anyway. So at that point, what is the point of a swappable system anyway? The other system that we also talked about was an umbilical, which Ben already spoke about a bit, and discussed the disadvantage of that system. So what we basically decided to do was not to necessarily invent the wheel, was to use the basis we had from the Apollo Bliss, which was a primary tank and a secondary tank, and introduce new technology and new systems to try to drop the weight as much as possible. And with that, we introduced composite tanks. Composite tanks are thinner, lighter, up to 30% lighter than all aluminum metal tanks, which were used in the Apollo Bliss. They're very high. Their very high tensile strength allows it to be light. Also, they have great stiffness to weight ratio along with strength to weight ratio. So it was good. We found something that could replace it, but we had to determine whether it was going to drop enough weight for it to even be used. So in order to do that, we had to determine how much oxygen would be needed by a astronaut on the surface of Mars. A human at rest is at average of 356 BTU per hour, and that requires about 550 liters of pure O2 per day at standard temperature and pressure. So assuming a linear relationship, I extrapolated to 1,000 BTUs per hour, which is the figure we're using for an astronaut to have during the EVA. And that goes about to 1,500 liters per day, multiply that by 1.5 for safety factor. We're about to 2,500 liters of O2 per day at standard temperature and pressure. So at this point, we knew how much oxygen we needed. We just had to see if there was anything out there that could meet our requirements. And that's where we contacted our industry partners at Paragon, Cobham, and Orbital ABK. And we were actually able to find examples that they are actually producing today that meet the requirements that we need. So for example, this example from Cobham would be at the 3,000 PSI level that we wanted to, can hold the 2,500 liters of oxygen that we wanted, and it would be about 7 pounds full weight on Earth, and secondary would be around 2 pounds on Earth. That's about 9 pounds in total, which is a stark difference from the 35 pounds that the Apollo Bliss used. There is one thing that this doesn't include the valves and the wiring that's needed for it to function. However, it's still going to be much lighter. And right here we actually have a 3D printer and laser cut version. This box represents just the exact dimension of the Apollo portable life support system. This would be the size of the secondary tank. Inside, this one would be the primary tank. This isn't this exact size of the purge system of the Apollo Bliss, but it's basically the way that it worked. It had 2 spherical canisters, both at 6,000 psi, all metal. And I'll show a 3D printed version, a CAD version. This holds half the amount of oxygen that this can hold, and it's way lighter than this system. And I'll show the CAD version. So this is the Apollo portable life support system on a mannequin. And as you can see, the top figure up here, that is the purge system. And right here is a comparison. This is a size comparison between our secondary design and the secondary design that the Apollo suit used. And as you can see, there's a huge difference in size, and this secondary, the one that uses COPD, holds twice as much oxygen as the one used in Apollo.
So thank you, Kevan. Next thing that we considered for our project was the battery. So as a quick recap as to what batteries were used before. So up till 1990, the silver zinc batteries were being used, the specifications for which are as given, 20.5 volts and 45 ampere hours. So like two notable places which had the silver zinc battery are as given. From 1990, it was decided that we would have a long life battery, and hence lithium-ion batteries started being used. So because they have a higher energy density, henceforth, that was their preferable battery. So for the purpose of our project, we decided we tried to find out the battery which can be easily obtained and is closest to what we need. So we came across this Nissan Leaf battery, the dimensions for which is given, and this is a laser cut version of it. We can even pass it around if you want.
The rough size.
This is the rough size. We will also be showing the CAD simulation for it. So as I mentioned, the reason we found it was, it was well packaged, it was easy to obtain, and it kind of meets a power requirement. Apart from using a battery like this, we also suggested a design modification, which was that up till now the battery was in the place, but what we are suggesting is let's take it to the suit, let's place it in front of the chest, and see if it works. So the benefits that would come with it is having a more stable center of gravity, as well as we would not be requiring an emergency battery system because the battery is in your suit. So in worst case, when you have to remove your bliss because of any emergency situations, your suit would still be powered. One problem with this kind of battery and placement is, so when a battery works, of course, heat is generated, and we are still not in a position to control that heat. So that is a point that we have to research further if we want to place the battery in the suit near the chest. Another concept that we are still thinking of, and we also consulted some industry partner with, was the concept of compressed air energy storage. So in this, basically, we would try to run a multi-stage axial turbine. So the concept is that because we have oxygen tanks which are pressurized at 3000 psi, and we have the suit which is at 4 psi, and the outside which is at 0.09 psi, considering such a pressure differential, if we are able to tap the pressure differential to run the blades of a turbine and generate electricity with it, which can be used to charge the battery, that would be good. However, the biggest problem with this, as we talked to one of our industry partners, Grant Anderson, was fire, because you are trying to send oxygen at 3000 psi through the blades of a turbine. In the past, this has happened. There have been equipments which have caught fire. So it was a special advice to us to look a lot into this before implementing it. So that we will take it from here.
Okay, so the next big responsibility of our team is making sure that the astronaut is kept at the right temperature. So this main consideration is taking the heat away from the astronaut when he's hot through wicking away his sweat through the protective layer of the suit. So this purple layer here is a protective layer that's directly on the skin, and it's also porous, allowing the sweat to go through, and it also goes through this permeable insulation, which is sort of like, you can think of it as Under Armour. It allows sweat to go through, but also keeps the astronaut warm, and based on the level of activity an astronaut might be doing one day or the temperature expected outside for the day, they can potentially change the thickness of that layer. And then next we have this wicking layer, we call it, and it would be like a wicking membrane that allows sweat to go through, but also can hold the pressure from this CO2. And basically, the sweat goes through that and then is evaporated into this air. And if we have this open system where CO2 is being pumped into and out of the suit that we've been talking about, this pressurized CO2 will be, as it goes out of the suit, so will the humidity in it from the sweat, and the heat will escape the suit, being purged out that way. So yeah, that's a description of the layers again. And then another thing we considered for taking the heat away from the body, if we end up doing a closed system, is that this approach would still work. We could have a slurper, which is basically a dehumidifier that also has a fan, so it would be circulating the CO2 inside the suit and dehumidifying it taking the sweat out of the air and storing it somewhere else. Okay, so one thing we wanted to make sure we didn't disregard is also heating and cooling the astronaut through liquid. Even though we have this open system and we've discovered this dense monolithic membrane, which is the wicking layer Natalie was talking about, it is kind of untested territory. You know, it depends on how much the astronaut sweats and how cold the gas is that's coming in. And what we do know is how well liquid cooling and heating works, because that's what they've done in the past. For the spacesuits, so if we're able to significantly cut the weight, we're considering having some sort of liquid cooling or heating supplementary to our open system cooling. So what's super great about liquid cooling is that it's the easiest to fine tune, so the astronaut himself can decide, oh, I'm feeling too hot, let me cool it down, or I'm too cold, let's heat it up. So that would obviously be the benefit of liquid cooling, whereas with the open system, it just kind of is what it is, depends on how much they sweat and their environment. The problem with liquid cooling, of course, is that you need a heater and some sort of cooling mechanism, and those can add significant weight to the bliss. Cooling would be done with either evaporation or like dry ice sublimation. Since we're not really going this path, we haven't looked into those too much. Yeah, but maybe we could find something that's smaller, kind of could just be supplementary to what we're doing with the open system. We did reach out to Paragon, Grant Anderson, about if we were to do liquid cooling, how CO2 swing bed works, and that's definitely one thing we want to look into more and try to understand better in case we end up going that path. So that's like a kind of flow chart of how it works, but right now we're more focused on the open system cooling.
So my portion of the project was CO2 removal, and the reason why we need CO2 removal is because when we breathe out, we're not actually using all the oxygen that we breathe in, so that we can actually recycle the air that the astronaut uses to stay alive. And so the current technology that's being used on the ISS spacesuit is lithium hydroxide canisters or metal oxide canisters. And the basic principle behind these canisters is that you force air into them, and then chemicals inside them will take the CO2 out of the ventilation loop. And so the problem with using lithium hydroxide is that often on like current space flights, they have to ship a ton of this lithium hydroxide over to like the ISS. And for any future Mars mission, you might have to, if you were to use lithium hydroxide, you'd have to ship a lot of it. And the better thing about the metal oxide technology is that you can actually regenerate the metal oxide that they use in the canister or like an oven that they have in the ISS. Although a problem with this, again, is that you'd have to, the metal oxide itself is actually kind of heavy. It's like 13 ounces, if I remember correctly. And so that would be kind of a big bother to have on your back all the time. And another basic issue with these is that since they're using chemicals that kind of either react or they're not really something that you can regenerate during your EVA, so they'd actually be a hard limit on how long you can stay out of your space. Like, it's possible that these canisters would just run out and then you'd have to go back to your base. And so the next generation of CO2 removal that's being researched is this system called the rapid cycle amine system. And the basic principle is that you have two sorbent beds, one that's constantly absorbing CO2 and another that's being regenerated. And so with these two beds, like, you can use them indefinitely. The only limit would be how much power you have. And so the basic principle is that you would absorb CO2 on the one bed, and then you cycle the two beds. So the second bed is then exposed to this vacuum, and then the pressure swing caused by this exposure to the vacuum causes the CO2 to absorb. And although that's good for use in space, in like the ISS, it's not really useful for Mars because of the really high partial pressure of CO2 in the Martian atmosphere. So there wouldn't be a significant pressure swing, and then the CO2 wouldn't be absorbed from the bed that you'd want to regenerate. But then the technology that seems most promising right now is the metabolic heat regenerated temperature swing adsorption bed, and that's being developed by Paragon, as mentioned by Franny earlier. And the basic idea behind this is that instead of using a pressure swing to desorb the CO2, you'd actually use a temperature swing. And so the temperature swing, like normally you'd have to heat up the bed to really high temperatures in order to get the CO2 to desorb. But with this technology, what they're looking at doing is cooling down the adsorbing bed to really low temperatures, and then reheating it to like the normal temperature so that you can desorb. And the way that they're looking to cool down the bed is by using liquid CO2 from the Martian environment. It'll be really easy to process, and there's a lot of it on there. And theoretically, it seems like a pretty good idea, but a problem that I see is that it would be dependent on how much liquid CO2 you have in your backpack. And so that would be a limiting factor in how long you can stay down here. And then my other section was trace contaminant control. So while CO2 is the main metabolic byproduct of like your breathing, there are also a couple other chemicals that you produce when you're breathing in and out. And a number of them are like formaldehyde, ammonia, and methanol. And so we need to get rid of these chemicals in your breathing loop, or else if they build up, they can cause irritation and just be really annoying. And so the current state-of-the-art technology is using activated charcoal to remove these. And activated charcoal, like lithium hydroxide or metal oxide, that's not something that you can regenerate during your EVA. So we tried looking at some other alternatives. One of them was to revitalize the activated charcoal beds. And the general principle behind this is that you would reheat them, and that would help desorb the things that are attached to it. A problem with this is that it'd be kind of hard to use during your EVA because you have to heat it up to pretty high temperatures, and that's just not something that's easy to do while you're in space or while you're outside of your base. And so it would be useful if you're able to return to your base, then you wouldn't have to constantly get new activated charcoal beds, but it's not something that we could do in the process of going outside. And so it'd be, again, like a limiting factor in how long you can stay. And then the other technology, well, not really technology, but the other alternative that we explored was just removing the trace contaminant control system entirely and relying on what we have to remove CO2. And the main problem with this is that it actually would the CO2 removal system isn't super effective for removing ammonia and formaldehyde. So you have the levels of those two chemicals would surpass the allowable limits. And then so to lower them past the allowable limits, you'd have to vent air continuously. So you'd have to make up for the lack of removal by just essentially getting rid of a bunch of it and then putting more oxygen into it. So whatever weight gains we get, we have to essentially like get rid of them by adding more O2 to the tank. And then the last section I had is environmental protection. Like Dr. K mentioned, if we're going to use an open loop system, we're going to be constantly intaking air and then outputting into the environment. So there are a lot of possibilities where our germs could leak into the Martian environment, or we could intake something that's potentially dangerous from the Martian environment. And so besides all the basic stuff that every space mission needs, like they sterilize all the probes really carefully, so as to ensure that nothing gets onto Mars or into space. We also have to make sure that we're not intaking or outputting any possibly dangerous things. And so the main thing that we were looking at was using antibacterial filters, and this is kind of just the technology behind like your normal air purifier. And so with really fine filters, we could get rid of pretty much everything that would be harmful. And a problem with this is that you have to replace a filter every once in a while, just like with your normal air purifier. And so we were also looking at some alternatives, like combining the filter with UV. And this is something that a lot of commercial air purifiers use again. And so with UV light, we could kill any germs that you're taking in or going out, or that are leaving your suit. But that would be a power cost, and it would also cause a lot of heat. So we're not sure if that's necessarily what we want.
Thank you, Zach. So in conclusion, I just want to mention the upcoming semesters. We want to shift our focus to prototyping and contracting out our design parts. This semester was a lot about high-level thinking, and going forward, we acknowledge that the key to making leaps and bounds in terms of progress is having something physical that we can work with, we can share with the rest of the other teams, and we can physically tweak. So one part, however, there are a lot of parts that we could not build, and we acknowledge that. We're a university-based team. We don't have limited funding. We don't have the research experience to say an organization that focuses on one of these parts. So we want to contract out as many parts as possible. An example of this is COPVs. I personally have experience with wrapping carbon fiber, and I can tell you that unless you have all of the hundreds of thousands of dollars worth of equipment to wrap carbon fiber effectively, you end up with a much lower quality product in reality than you do in theory. So it makes sense to just contract it out. And we've already begun talks with several COPV manufacturers, Kayvon mentioned, that could potentially make the parts we need. Second, as Juan said, we want to talk about exploring modern compressor developments further and possibly designing our compressor and having it made for us. And finally, we want to look at smaller, less obvious components for weight-saving opportunities, pipes, wiring, valves. The technology for all of these has advanced in the same way that the more major components technology has advanced. We simply didn't pay as much attention to them because they didn't offer as large of an opportunity to cut weight. Are there any questions? No? Dr. K?
Yeah, what about your contaminants if they're not coming off the torso? In traditional suits, the contaminants are coming off the body and they're circulating in the breathing air. But when you split the helmet from the rest of the torso, you eliminate 85% of the area where you generate stuff. It goes out another way.
Yeah. So I guess the ventilation loop would just be like cut off from the rest of like the places that would be outputting things. Whereas like in a traditional suit, you have your helmet area is really the same. So that would remove a lot of the. Do I have to answer any questions? Or is there like...
I don't know if there's any questions online. Nobody said anything. I think they can. You might ask.
You have low battery.
Well,
No one has sent anything. Oh, wait, there was one message. No hard feelings from Grant Anderson.
so who's next?
So group 6, I believe, is 7. What team are you guys? Software, right. The key to having a successful MarsSuit. So I'm going to welcome software up, and they're going to talk about.
Oh, 6.
Yeah, I thought we were doing team 6 first. Okay. So team 6, materials.
Yeah, my flippant response there was just there's no hard feelings that they didn't use the MTSA.
Is that Grant?
Yeah, I was just saying my flippant response was my no hard feelings is about them not using the MTSA.
Oh, we will use it eventually, but not yet.
Yeah, I was, like I said, no hard feelings.
Thank you, Grant. What? 10%?
I think I have a battery. I think I have a little battery pack. Let me see if I have it.
I know.
Sure. Yeah. Do you have his number? Yeah, I think we're gonna phone it. Cool. But we could use if you have a charger. You can set one of these right next to me. Do you have the charger? I'm sure someone will have an iPhone. Does anybody have? Ben, are you using that?
Yeah, but not both plugs.
No, the charger. Does anyone have an extra lightning cable?
Does it have a lightning cable?
Cable? Yeah, I got it.
Oh, okay. I don't know how close. Does anybody have a USB port? To charge this?
Oh, I've got
Wait, yeah, just use Ben's.
If he wants to charge his phone.
Hello, we are Team 6, and I'm Jonathan. We have Lucy here, and I'll be presenting on behalf of Reed. And we'll go through historical material uses in suits from Apollo missions to international space missions. We'll also talk about managing moisture within the suit, and then we'll get into trying to bring some of these materials and some of these prototyping methods into the real world. So we'll start right off with Reed's contribution, which is bringing a list together so that future classes have an understanding of what kind of materials have been historically relevant. Reed started talking about a design method that we could follow to start testing whether or not one material is of use to us or not. And we quickly can go through. The first step is to break material selection up by layers. So we can talk more about which layers we're talking about. And then additionally, determine which material property is needed per layer. Next, we try to look to reverse engineer solutions that have already been created. And this would be in existing suits, spacesuits, and it also could be in other industries. And then once we've done so, we can identify a material that we are interested in. We can start to prototype this material and ultimately test this material with the ultimate goal of then feeding back anything we've learned with this test to identify or alter the original material. If we were to break down the suit into a number of layers, you can find we've got a pressure bladder on one side, a thermal control layer, basic insulation, additional insulation, and an outer covering. But more generally, we can break down the layers into a pressure suit, cooling and ventilation, and thermal mechanical garment on the outside. And if we want, having identified these three regions, we can now present lists with materials that have been used in these areas and their functionality, as well as their success or failures. Here in the first list, each individual line is less important. More important is the status when this layer was used. For example, it was used in a prior Apollo mission, or if it's suggested for a future Mars mission, and what type of layer is, what the material is, good, bad properties, and ultimately what it's going to be used for. So we've got three different lists, one for the pressure suit, one for the cooling and ventilation suit, I should say a layer rather than a suit, and one for the thermomechanical garment, which includes, among other things, the insulation, but also layers that could resist damage to the astronaut, such as like a layer to prevent fire, a layer to prevent collisions and whatnot. Having gone through these lists and having done research on past suits, Reed found out that in general there's certain trends with how one material gets transferred from one suit to the next, and whether the material gets nixed from the layer. Some of the causes for a new material or an old material to be used on a suit have been oversight in the previous design. Is it flammable? Is it not flammable? changes to design requirements. Now that we're going to Mars, we're going to need all new materials in general. And improvements in technology. Sometimes, in our case, maybe that means removing the cooling, the liquid cooling, and then also removing or accomplishing one task with one or many tasks with one layer. So I'll pass it on now to Lucy. We'll talk more about managing moisture.
Now I'm going to talk about the two solutions to manage moisture to optimize the climate comfort. So that's first. The first one is a weak material. Actually, it is just directly to remove the moisture from the field. So we can imagine a situation on Earth, the human on Earth, when you feel it's really hot. What are you going to do? If you still have some clothing inside, you just take off your clothes. And when you feel cold again, just take out them again. But on Mars, as an astronaut wearing a spacesuit, you cannot do that when you feel really hot. You cannot take off your spacesuit. It protects you from the from UV, from whatever. So as this situation happens, one solution to solve it is to use the wicking material. It just directly remove moisture from skin. It utilizes a principle called the capillary reaction. It just means this fabric is made up of so many tiny tubes, and just like capillaries in your body, the moisture can be moved away from your skin and released to the air or the outer layer of your clothing. So let's zoom in to see the capillary reaction. Let's take a look at this example. There are several tubes with different internal diameters. They are put inside a huge tank, and this tank is filled with green-colored water. And let's see, those different tubes have different internal diameter, and the water inside will climb up to different levels of height. That is just the capillary reaction because of the different internal diameter. Let's zoom in one tube to see. So that is actually happen under three kind of forces, which is the adhesion, cohesion, and surface tension in between the water molecule or between the water molecule and the tube molecule. And there's also a curved shape because this adhesion force drags the water upward. Okay, making use of this capillary reaction, the wicking material gonna work. And I also did some researches on some existing or proposed good solutions of like if you want to build a good wicking material system, what kind of components that you should consider about. So the first layer is the thermoplastic elastomer film. We call it PE film, and it is a one-way water vapor transport wicking material. It can maximize the water vapor transmission. But for this single layer, that is not enough. The second layer is a super absorbent polymer, we call it SAP, which can maximize shear modulus and whatever. And the third layer is LCBG fabric, which is compatible with the previous two, which can maximize the thermal conductivity and capacity. So those three layers should be combined together. Let's see a CAD work. The green color is the TPE film, and that purple layer is the super absorbent polymer. And that two red layer is the polypropylene, which is the LCBG fabric layer. So that is one CAD modeling. Okay, that is totally for one solution. Just to do, okay, you can sweat. When you sweat a lot, we just will remove your sweat in a quick way. That is for the previous solution. Another solution is called the PCM technology, the phase change materials. It is just like, let's take a look at this example. This is milk tea, which is one of my favorite drinks. So what is inside the glass circle? It's ice. I always ask the the cashier putting give me more ice. This what is function of the ice in this drink? This just want to maintain constant temperature of your drink to give you a good flavor. So the ice here it's also a phase changing materials. The freezing point of the ice is 0 Celsius. It will absorb the heat when the drink tends to get hotter. So we can also take a look at this video. This is a video created by a company called Outlast Technologies. So this is your skin. Your skin gets hotter, and this material is going to absorb your heat. And it works like a heat sink and store the heat. And when you get colder, it just release the heat to your skin to warm you up. So it's like this material is just like a heat sink. An interesting thing is this technology is just patented by this company called Outlast Technologies, and this technology is developed for NASA. And the interesting thing is there's another startup called Ministry of Supply, and it's just a license. Okay, they want to manufacture a type of clothes, and they reach out to Outlast Technology, this company. Can I use this ECM technology? Okay, pay me some money, and I will license you to use it. And later on, this company built a shirt called Apollo shirt, and it sells very well. Just making use of this type of technology. It is not the single technology that we apply the spacesuit technology into our daily use. Another example can be the memory foam. It usually exists in your pillow or your mattress. That is another example. Here are two tests that is conducted by this Outlast company. The first one, this shows someone does not wear the Outlast material. This shows someone wears the material. And the blue color shows it is dry, and this red color shows it is humid. And you can see the closer away from your heart, that the more humidity you are going to generate. But when you wear on this Outlast material, this PCM material, it looks just totally green with some blue, totally blue with some little bit green. That is a good situation. Makes you feel comfortable. Another test that this company did is to record the humidity that you generate within a time range. In this case, it is from 0 to 5 hours and 40 minutes. And this blue color line shows it is someone, the sample people just wear traditional material, and the red line shows it is an Outlast material sample group. And you can see that those group of people just generate relatively smaller amount of the sweat. That's a good news. So that is the whole the two solutions that I did research for. Talk about our material testing.
Knowing that we're designing for an astronaut who is a human and has human needs, I wanted to get to putting some of these materials into real world tests as soon as possible. There's some, as we've outlined previously with this basic design process, we need testing to then decide whether or not a material is useful. But there are some challenges with testing. Mainly Boris was very strict on telling us that we weren't allowed to do any human testing. Originally, we were excited about sticking your hand in a box and increasing pressure until you're uncomfortable, as one example. But we were quick to nix this idea in favor of maybe something that's a little more FDA approved. I'm personally interested in the pressure garments because I know it's crucial to the design of the K-suit. To look more into the materials of the pressure garments, previously talked about some of the experiences I had on campus where I was in a pressure-filled suit that was next to my body for several hours and next to my body during high exertion periods. This is very appropriate because it's like a blue-collar activity you might be involved with on moving. A sphygmomanometer where I could increase pressure on my arm and then tell whether or not this pressure was appropriate for somebody that might be working within one of these suits. The most basic test being increased pressure and understand at which point you become rather uncomfortable and dysfunctional. And that happens to be just below 15 millimeters of mercury, which is about 1 psi. And so it's important to note if we are going to have pressure next to the skin, it must be spread out to avoid some of these pains. Using this sphygmomanometer as more of a test bench, you can then start to use other materials that you might have on hand, like this rubber silicone, which is easily mixed with 2 parts and cures within half an hour, and is then capable of forming shapes and making rapid prototyping possible, much the way that 3D printing is possible for rigid material. So in this case, as rapid prototyping, just a silicon rubber piece to go around the wrist to mimic a pressure bladder and to interface with tubes, channels that could either take fluid or carry cabling, as an example. So in general, I think it's important to include not only the basic functionality of these materials, but to start integrating questions of comfort and biocompatibility with the human as early and as often as possible. Thank you. Any questions?
Yeah, you have that animation slide that shows the.
Yeah, we've got the backup slide, right?
I think Michael or one of the other students put together an animation slide showing the material. You have it out?
Yeah, I mean, I sent it to you. Did you guys get it?
They're in the. Did you put the link on the backup slide? We didn't. Okay. It's supposed to be in our backup slides, but we can pull it up if needed.
Part of the main presentation because it helps people visualize. You don't have it on you, do you, Alex?
I have it on Drive. Send me a link. What's in your email?
Yeah. Okay.
I mean, if it's a big deal, don't worry about it. Just put it in the final report.
Yeah.
So I think it's good because it's good to visualize it. In fact, I'd like to use it in Washington.
Okay.
To show it.
I was hesitant to use it personally because I don't understand the full intent of the animation. But if you being a creator would love to present it, I think it would be effective.
If you want.
Do it now.
Can you like type it?
Everybody thinks it's worth using. That's not hooked up.
Hello? Working? Hello? Okay, so earlier Professor K showed us a nice little, Dr. K showed us this little slideshow animation funny sounds. And I was like, get a little better. So this is a little, I was messing around with this little physics simulation sandbox thing. We get a kind of this just shows a little stick figure with a separation between the helmet, which uses oxygen, O2, and we can see that the O2 doesn't leave the system, right? But then the body is pressurized by atmospheric CO2, and we can see it flows through and out. It's just a very simple, but it's like it moves, and then we can view. Here it's going to do it. Show pressure. So we can see that there's a pressure high in the suit compared to the atmosphere. And then there is I made another little animation for demonstrating the possibility of using the dense monolithic membrane material, which would allow us to sweat through while still holding gas pressure. So if you just ignore the stuff on the right side, that's just to show like skin and sweating through. And then right here, this is supposed to be the dense monolithic membrane, where this area is red, so it holds high pressure. So your skin feels the pressure, but then the liquid or vapor or the water vapor will pass through the dense monolithic membrane and then lead into a low pressure area where it will turn into frost on the outside of your suit. It will help mass transfer and cooling while still maintaining pressure. It'll also increase the comfort of the wearer because work for 8 hours and sweating is not comfortable. Do you have a question or just straight?
Yeah, I have a question.
Okay, go ahead.
How did you make it? Is this yours?
This is called powder toy. I used to play with this when I was in high school. I'm a nerd. So
Excellent.
yeah, it's a lot of fun. You should try it. It's like there's all kinds of fun little things you can do with it. But I thought I was like procrastinating. I was like, oh, I can make something fun with it. So this you can see that the liquid water will pass, and then let's see. Earlier on, we saw that this area is blue. So blue is low pressure. So with the lower pressure, the water easily vaporizes, and then it turns to frost.
I'm assuming like it's all scientifically accurate, right? So if you put the right actions.
Yeah, but you can't control numerically. So you kind of like place little elements and do certain things. So, but it's all in real time. It's kind of fun. And then it's actually quite accurate. Like it has densities and phases and different interactions between different elements. So you can mess around with it. You can create a better animation than mine. It's just for fun. So that kind of demonstrates the idea. So yeah. Any questions?
I think that's a pretty good tool to use.
Yeah.
Explaining this.
So here's some screenshots. Okay.
Any other questions? Okay, software guys, you're next.
Hello. Hi. Yeah. I'm not home. I'm really busy. Is there like any other car you guys can use? I mean, is there? Eric doesn't know where the key is. Andy. Okay. Tell him where the mail is.
7. Name's Michael. My name's Michael. This is Ethan, Sebastian, Seth, and Will. So just an overview of our tasks this semester. They're basically software support for the torso and the PLIS teams. The first, our primary task was to work on the MetMan heat transfer model, which is a low resolution finite difference model for heat transfer between different layers of the body. We completed compilation and execution of the Fortran code, and we also created a web-based graphic user interface. Our second task is to work on Legacy and Violet, which is a program that tracks different consumables and displays critical parameters, alerts to the astronaut. So first, the MetMan heat transfer model was originally given to us, and it was worked on by Dr. K in his PhD research, and it was also used by NASA Johnson Space Center. It was originally programmed to model traditional suits for either the ISS or the moon, and we do need to go into the source code and change it up because in the code it assumes that the helmet and the torso are connected, whereas in the K-suit, they're separate. So we do need to change that source code feature. There are 41 total nodes. There's 10 body segments. Here's head and torso, 2 arms, 2 hands, 2 legs, and 2 feet. So there's 4 layers each. It's the skin, the fat, the muscle, and the core. So that makes 40 nodes. And finally, there's a 41st node for the central blood. And the reason why we want to use these models is because it's very difficult to test different materials or different prototypes under the conditions that we want. For example, if we want very low pressure and there's very low pressure atmosphere, it's very difficult or expensive to get those type of environments here on Earth. And we can also check feasibility, optimality of certain design, such as different materials before actually spending money and going out and buying it. So this just lays out the heat transfer throughout the system. So as I said before, there's 4 layers in each node: the skin, the fat, and muscle, and the core. So there is heat transfer modeled between each of the adjacent layers. And there's also the central blood system, which has heat transfer throughout all 4 layers. Finally, here's the major heat transfer. It's from the skin to the external environment.
All right, so just to give you guys an idea of generally what the software project entails. So the MetMan, as you mentioned earlier, is a 41-node finite difference thermodynamic approximation of a given in a spacesuit. But when we went through the source code, there's a lot of variables, a lot of parameters. The documentation ended up being almost 300 pages. So a lot of what we did throughout the semester was going through, figuring out what each variable meant and how that affects how that's affected by any spacesuit design. So here's a lot of the important ones that we did. Human parameters right here, these are general constants given by NASA. Things like convective and radiative area, basically your skin surface area, useful work efficiency, height and weight, etc. Those are all of your astronaut and what you can generally expect on a given person. Then things like undergarment and liquid cooled garment, those are things we change when we're given designs by the design team. So someone comes up and they say, our torso is going to use, dermant and, plastics, so, whatever materials they give us, polyethylene, and we plug in their conductivity, thickness, emissivity, and we can run the program and tell people, you're going to have your hand overheating, or you're going to have, pressure differentials too high between your torso and your legs, things like that. And then suit internal environment, these are generally fixed because we've decided for the most part on what our gas flow rate are, and specificity of gas, total pressure, oxygen pressure, all that kind of thing is internal suit, and suit composition, much like undergarment and cooling garment, are more factors that were given by design teams. So a lot of what this is us prototyping designs, and people give us designs, we say, here's where it works, here's where it doesn't work, here's what you guys need to do to improve this design, and it's really efficient to do that without having to build a full model and run diagnostic tests. And then when we, go to the next slide. When we get designs out, you'll see we have a way to run this. So when you get designs out, here's some of the outputs we get. You get temperature of head, temperature of core, all those other things to make sure you're not getting
frostbite or hypothermia or overheating and fever, dehydration, all those kinds of things. Good. So you get all these things, latent heat loss, evaporation, and here are our safe temperatures. So we want our head core temperature, which is generally your body temperature, to be around 98.6, which is healthy. And then temperature of your skin can't be below 70 degrees, because then you have, or around 70 degrees, you have problems like that. And shiver rate is how often you're shivering. You want to keep that basically to 0, because if you're shivering, you're losing heat inefficiently and all kinds of other things that are unhealthy. So with that, I hand it off to Will, and we'll do graphics.
Okay, so the point was to make the graphic user interface so that the other teams would be able to interact with this program without having to install any type of code compilation like Java or Fortran. So the first version of this GUI was built in Java, but after preliminary testing, we decided that it would be too inefficient because everyone that needs to use it would have to install Java, which would take a really long time and be kind of complicated. So for the second half of the semester, I worked on moving this to a web server. So I'm currently running a EC2 instance on an Amazon Web Service. It's a free instance, so sometimes this may lag, but hopefully right now it's fine. So all you do is you press on whichever mode you want to run. So we have mode 0, 1, and 2. There's a description about what this mode does. And currently mode 1 is not supported, but we're going to be working on mode 2 for the majority of this project, so it should be. So we have these input fields, and these are what the code reads. So basically the server takes all these input fields, it creates a file, and runs the Fortran code based on this input file. Because of the nature of this Fortran program, the server can only handle one request at a time. So like there can't be 2 people on the same website doing it at the same time. So that shouldn't be a problem for the testing case. So you basically fill it out. We have some example inputs right now because we don't really have it originally. But you just press run, and it runs the program. So right now it's pretty fast. So you can see this is like the output file that the Fortran program produces. The next step would probably be to create some type of parsing program that can understand this output and give a preliminary, like whether or not the spacesuit is safe, or if it's not safe, what parts are failing. You can just select another mode, run these inputs, and it'll give you the result. For mode 1 right now, if you run it, there's an error. But if it's really required, we can really implement this in just a couple of minutes. You want to talk about these?
Yeah, so really quickly, just some of the output parameters that are pretty critical. Like we said earlier, we get inlet and output water temperatures for the LCG. And most importantly, we have like a log of the temperatures, like a time log of temperatures throughout simulation.
I think that's for each of the 41 nodes, actually. Yeah. And so you can see they're all like 99.7, 95.5, 100.5 degrees. So these are all well within our healthy range. Nothing exceptionally cold. If you look at the bottom, there are some temperatures that we would not be wanting. Something like 0.75 times 10 to the second. That's about 75 degrees. But if that's skin temperature, that's more acceptable. So those are all the outputs of any given node.
So another problem that Mars poses is the need for an autonomous life support system. In current and past missions, you can rely on the ground control on Earth because the communication time is fast enough that an astronaut can ask a question and receive an answer very quickly. That's not feasible on Mars, however, because of the radio delay to actually send that question and then also wait for the answer to come back. The one-way times is anywhere from 4 to 24 minutes. So obviously in a critical situation, not near fast enough to be of use. And for example, in the Curiosity mission, it was about a 14-minute delay. And these are just one-way times. So in a Q&A scenario, this would actually be anywhere from 8 to 48 minutes. And so the solution to this is a couple of NASA programs called Legacy and Pilot. Legacy is a program that uses biosensors to monitor critical parameters such as heart rate, temperature, etc., and then uses that to compute the metabolic rate of the astronaut. And once you have the metabolic rate, you can then track and predict the burn rate for consumables. So, like, the most important one is usually oxygen. Once you know their metabolic rate, how fast they're consuming oxygen, predict that at that current rate, what are they doing, working, walking, etc. How much longer do they have, and how far can they venture away from their base before they have to turn back? And then Violet is the program that actually allows the astronaut to interact with Legacy. So Legacy is the brains, is computing all of this behind the scenes. And Violet is a speech recognition program that actually will say results to the astronaut and also can receive commands via voice. So you can ask for things like, how much time do I have before I need to head back, etc. And these two programs combine to act as the mission control that astronauts typically use back on Earth. This is the functional diagram of Legacy and Violet. The key here is to see that metabolic rate is actually computed 5 times independently. That's for robustness. So you don't have to rely on one sensor and then having out-of-whack results saying that you have plenty of oxygen left when really you don't. So you actually have a lot of robustness built in with those 5 metabolic rates. Those are combined with statistical methods to produce the best rate. And then from that, you can calculate your consumable management and everything else. And here you can see also there's user prompted and then also alerts. So the user prompted is if you ask Violet, how much time do I have left before I have to go back, things like that. That's all prompted by the user and can be understood by Violet. And then the alerts are going to be things that have thresholds set. If you get below a certain level of oxygen, etc., and you'll automatically receive an alert from Violet that you need to head back. And this is a video of these. This is a video of these 2 programs being tested at Johnson Space Center. You can see they're having the astronaut move around and do physical activities similar to what we've done here in the UK. Then they're tracking all of the bio data and then producing the metabolic rate.
So what we were able to accomplish this semester, so we were able to take the raw and outdated Fortran files and get them compiled as exe files, as executable files that are now fully functioning. This was harder than we expected. It took a lot of trial and error. So at the end, we weren't able to get the Fortran files running on Mac OS systems, which was unfortunate. But we were also able to successfully execute Mode 2 and Mode 0, the Mode 2 and Mode 0 input files, which were the EVA suit and the undergarment respectively. And so now those can be manipulated and extended and added to, and most importantly, used for feature analysis. We'll develop that web-based GUI that is now available for MetMan, and so now you don't have to mess around with the input text files that are really annoying. And in our documentation, which is going to be up on the Epic Challenge website, we very concisely summarize MetMan, the GUI that will design Legacy and Violet, and outlined what our status on each of those facets, what needs to be done, and just some short little summaries to catch people up to date. And so future work, and for future software teams, what needs to be done. So first of all, with MetMan, the code needs to be customized, and like we said, that the head and the torso, we're messing around with that, so the code obviously isn't going to fit for that. So that needs to be customized and enhanced for better performance. And then the visualization output, which we didn't have enough time to get to this semester, but that needs to be implemented so that there could be like an easy way to like visualize the data in like an aesthetically pleasing manner. And then in terms of legacy and Violet, we took a preliminary crack at trying to get that code to execute, but we were unsuccessful. And so the compilation and execution of that code would be the first step, and that'd be pretty pertinent and crucial. And then from that point on, there would be a lot of communication that would have to be done between the helmet team and the torso team in terms of implementing the sensors and the head-up display that the helmet team talked about earlier. But beyond these specifications, for future software teams, it's pretty much open-ended as to what they want to do to optimize the performance and create efficient and viable end product.
Bravo.
Questions?
Bravo. Great, guys. One question I had is if you move the execution offline, then why does it matter if you have a Mac?
It doesn't matter anymore. That's the whole problem.
Yeah,
It doesn't matter.
You can't run the executable file on a Mac, but you can go to the website.
But now you can use it off.
Right.
Yes.
So basically what he did is he basically rented out an Amazon server.
It's a Windows server, so we're able to execute the exe in that Windows server, and you'll be able to work with the exe through any.
So really,
So now you can
matter.
access it.
So what is that site?
It's metman.localtunnel.me.
You know what you might do? You might give that to Sean. Yes, Sean is distributing what we're doing to everybody. So, in exchange for a GoFundMe, you have the site. You want to run it? You want to play with it? Here it is. You need a password?
No, but I think it might be susceptible to like rejection tax. There's not.
I don't think anyone really goes to take that.
So yeah. But I don't know if that's going to be
Hey, thanks. That was great, guys. That was great. Okay, Sean, you're up.
Last group.
Oh, that was a very long presentation we had today. So